Good morning, friends and respected sir. Today we are going to present a topic on quantization of electromagnetic field. The presentation flow will be as follows. First, we will discuss about electromagnetic radiation, then about matter fields, and then about on quantum electrodynamics. And later on, the mathematical aspects will be explained by my teammate. So let's get started. 42 years after Young proved that light traveled as a wave, the French physicist Fizeau measured the speed of light to be just under 300,000 km per second. Over that period and into the 1860s, people like Michael Faraday, Andre Ampere, and James Maxwell and others were studying electric and magnetic fields because waves were known to need a medium to propagate through, like water waves or sound through air. It was assumed that all space was filled with a massless substance that was given the name ether. Then, in the mid 1800s, Maxwell proposed that the existence of an electric charge filled empty space with an electric field. Here is a NASA picture of small threads suspended in an oil aligned with the electric field of a charge. Accelerating the charge causes the electric field to change. Furthermore, he showed that a changing electric field created a magnetic field, and a changing magnetic field created an electric field. So, the accelerated electron creates a disturbance in the electric field that propagates itself through space as an electromagnetic wave. Earlier, Faraday had measured the resistance of empty space to the forming of an electric field called permittivity, and Ampere had measured the resistance of empty space to the forming of a magnetic field called permeability. In 1864, using their numbers, Maxwell calculated the speed of his waves. He found that the velocity was in agreement with Fizeau's for light. He had demonstrated that light is indeed an electromagnetic wave. The idea of an ether filling otherwise empty space was rendered unneeded for light propagation once electromagnetic radiation was understood. So it faded from our vocabulary, replaced by the idea that empty space supported magnetic and electric fields, and light represented a disturbance in the electric field. The exact characteristics of so-called empty space will be a recurring subject for us as we approach our study on the Higgs boson. Here is a simple wave. It has a repeating cycle, a wavelength, and a frequency in cycles per second. Here we see the full electromagnetic spectrum with visible light in the middle. Light with longer wavelengths and smaller frequencies than red light are called infrared. Radiation with longer wavelengths than infrared are called microwaves, and still longer wavelengths are called radio waves. Moving up to the energy scale, radiation with shorter wavelengths than violet light is called ultraviolet. Still shorter wavelengths are called X-rays, and maximum energy radiations are called gamma rays. We know that particles with electric charge create an electromagnetic field around themselves that stretches out in all directions. This field is attached to the particle. It will go where the particle goes. In quantum field theory, fields like this are quantized. That is, they contain tiny, massless, energyless bits of the field. We have seen that the photon is a certain type of disturbance, an excitation or vibration in the electromagnetic field. We will call them a localized vibrating ripple. It moves with a life of its own. It is not attached to the particle that created and sustains the field. The photon has no mass, no charge, a spin of 1, a boson, and travels at the speed of light in a vacuum. When we studied atom in our earlier classes, we saw that energy was quantized and equal to Planck's constant times the photon's frequency. Now we take a leap. If a photon is actually a localized vibrating ripple in the quantized EM field, why not consider the electron to be a localized vibrating ripple in quantized matter field, a field that permeates all the space in the universe? This is not as odd as it might look. As we know, the wave properties of the electron and how its behavior is described by the Schrödinger wave equation. Also, we know that how electrons and positrons can materialize at any point in space. What's happening is that the photon has distributed the electron field to the point that it generates the kind of waves that constitutes electrons. A convenient way to illustrate elementary particle interactions is to use Feynman diagrams, invented by Richard Feynman in 1948. Straight lines are for fermions, squiggly lines are for force particle bosons, and the back arrow on a fermion indicates an antiparticle. This is what quantum field theory is all about. These fields generate particles. You can't have a particle without a field, and every field will have its particle. Elementary bosons, force particles, require force fields. Elementary fermions, matter particles, requires matter fields. In modern physics, there is no such thing as empty space. Fields pervade space. They are a condition of or property of space. You can't have space without fields. Here is a couple of examples of how this electromagnetic force works. When two electrons approach each other, their charge generates a disturbance in the electromagnetic field. This disturbance pushes them apart and their paths are bent outwards. The same is true if an electron and a positron pass near each other. The disturbance in this case is similar in type but different in its details, with the result that the oppositely charged electron and positrons are attached to each other, their paths are bent inward. Here's the Feynman diagram of an electron-electron interaction where the photon's field mediates the force that changes the momentum of the two electrons. One says they exchange virtual photons, but this is just jargon. The diagram is used for convenience. A virtual particle is not a particle at all. So what is a particle? A particle is a nice regular ripple in a field, one that can travel smoothly and effortlessly through space. This virtual particle is a disturbance in a field that will never be found on its own, but instead is something that is caused by the presence of other particles, often of other fields. This kind of disturbance will decay or break apart once its cause is gone. This kind of interaction between the electromagnetic field and the electron field is important because the force that the two charged particles exert on each other, the Coulomb force, is generated by this interaction. This force is the first of four fundamental forces in nature. They are characterized by a coupling constant. The coupling constant for the electromagnetic force is 1 over 137. We use this electromagnetic force as a model for the strong and weak nuclear forces. The complete picture of what is going on is still an active area of research called quantum electrodynamics, or QED for short. Steven Weinberg, a theoretical physicist, summed up what we learned from QED very nicely. Just as there is an electromagnetic field whose energy and momentum come in tiny bundles called photons, so there is also an electron field whose energy and momentum and electric charge are found in the bundles we call electrons. And likewise, for every species of elementary particle, the basic ingredient of nature are fields. Particles are derivative phenomena.